Hello, everyone, and welcome to the United Nations University Institute for Water, Environment, and Health Science Talk Series in this, our 30th anniversary year. My name is Jenna Al-Sharafa. I'm UNU-INWEH's Youth Fellow, Diplomacy and Sustainable Development, and I'm delighted to be your host for today's Science Talk. For those of you who are joining for the first time, our Science Talks showcase the diverse, policy-relevant, and interdisciplinary research for UNU-INWEH and our global network of experts. These sessions are designed not only to share cutting-edge science, but also to explore how the science translates into real-world solutions for water, environment, and health challenges around the globe. Today's session, like all of our talks, is being recorded. The video will be made available in an open access format following the event, and you can find recordings of all previous science talks on demand via our website and YouTube channel at unu.edu/inweh/science-talks. As always, we will conclude with an interactive Q&A session. Please feel free to post your questions in the chat at any point during the presentation, and we will address as many as possible towards the end of today's chat. Today's science talk is entitled Environmental Controls on the Conversion of Nutrients to Chlorophyll in Global Lakes. And it is my great pleasure to introduce today's speaker, Dr. Roohollah Noori. Dr. Noori completed his PhD in environmental engineering at the University of Tehran in 2012 and subsequently joined the university's faculty in 2014. In early 2026, he transitioned into the Ningin Institute of Geography and Limnology, Chinese Academy of Science, NIGLAS, where his research focuses on freshwater pollution and lake ecosystem processes. He also served as a senior scientist at UNU-INWEH with specialization in environmental pollution and hydroinformatics. Please join me in welcoming Dr. Noori for today's science talk. Over to you, Dr. Noori.
Nice talk.
Yes.
Hello, everyone. It's my pleasure to present my research entitled Environmental Controls on Conversion of Nutrients to Chlorophyll in Global Lakes. About the research question, what's the eutrophication? Eutrophication is overabundance of nutrients in aquatic ecosystem which stimulates algal growth. These nutrients mainly originated from fertilizer in farmlands and soil erosion, which both are projected to increase in the futures. Lake productivity is expected to increase by 150% to 300% by 2050 and 200% to 500% by the end of the century. I selected some figures from the webs that show the consequence of eutrophication and eutrophication problem in freshwater inland waters, freshwater, a river near Chengdu in China, a bloom event in the Lake Taihu in 2017. Another figure shows the Lake Dianqi in China in 2010. And another figure that is the lakes in the Asia that covered by the green algal. When we talk about the eutrophication, we need to talk about natural eutrophication and cultural eutrophication. Natural eutrophication, the process of eutrophication is natural for many lakes. As they age over centuries, there is a build-up nutrient sediment, as shown in these figures. Sediment and plants material which slowly feed the lake basin. Eventually, the process ends and the basin becomes colonized by terrestrial vegetation. Timing of natural eutrophication, it varies between the century, thousands, and even more. But cultural eutrophication is human-induced eutrophication. Human activity have greatly increased the pace at which eutrophication can occur. The process for natural and cultural eutrophication is the same, but the main difference in the time. The time scale for cultural eutrophication is the order of decades. When we talk about the eutrophication, we can classify eutrophication in different classes: oligotrophic, mesotrophic, eutrophic, and hypereutrophic. Oligotrophic, characterized by low nutrient levels and high water clarity. Mesotrophic, intermediate nutrient levels lead to moderate productivity and biodiversity. Eutrophic, high nutrient level results in increased plants and algal growth. And finally, hypereutrophic is extremely high nutrient levels cause excessive algal growth and severe oxygen depletion, as shown in classes in this figure, in the right side of this slide. There are many classification systems for dividing the eutrophication to different classes, such as oligotrophic, mesotrophic, eutrophic, and hypereutrophic. Based on the main indicator of eutrophication, such as chlorophyll-a, total phosphorus, TP, total nitrogen, and secchi depth, we can classify each lake into one of these classes of eutrophication. For example, for oligotrophic lake, if chlorophyll is less than 2 microgram per liter, the lake is oligotrophic. If chlorophyll vary between 2 to 7 microgram per liter, the lake is in a mesotrophic state. And also, we can use total phosphorus concentration, total nitrogen concentration, and secchi depths as an indicator of eutrophication. And based on the different range of this parameter, we can classify the lake to oligotrophic, mesotrophic, eutrophic, and hypereutrophic. Another important point regarding eutrophication is limiting nutrient. That means which nutrient limit algal growth or productivity of the lakes. We use usually Tn, total nitrogen, to Tp ratio, Tn Tp ratio for determining the limiting nutrient in freshwater ecosystem. For example, if Tn Tp ratio is less than 9, the nitrogen play a key role in algal growth. If Tn Tp ratio varies between 9 to 22.6, then we have a co-limitation of both nitrogen and phosphorus for limiting the algal growth. If the Tn to Tp ratio above 22.6, then we have a phosphorus as a limiting factor of algal growth in the freshwater ecosystems. Eutrophication has many negative consequences for freshwater ecosystem and also for brackish and coastal water. For example, the main consequence of eutrophication is oxygen depletion. Algae acts exactly as a plant in the nighttime, consume oxygen in the water column and deplete, dissolve oxygen in the water column. That causes widespread fish kills. And also another consequence of eutrophication is byproduct of algae. Some of these byproducts are toxic and can harm human and other living organisms in the water column. Also, another consequence of eutrophication is decreasing water clarity. By decreasing water clarity, this can limit light penetration in the water column and decrease the biodiversity in aquatic ecosystem. Another consequence of eutrophication is greenhouse gas emission from the lakes. Lakes are emission hotspot of greenhouse gases to the atmosphere. Greenhouse gas emission from lakes are equivalent to 20% of global CO2 fossil fuel emission. Another important point of negative consequence of eutrophication is economic loss. For example, a study conducted across the United States show a total economic loss between 2.2 to 4.6 billion USD annually from the eutrophication in freshwater ecosystem in the USA. This economic loss mainly is from water treatment costs, about 1 billion USD per year, recreation losses around 1.1 billion per year, USD per year, and property value decline around 1.3 billion USD per year, and other impacts such as health ecosystem and damage. In a global scale, for example, in China per bloom in China billions of yuan per bloom per each blooms, and for the Baltic Sea the economic loss is around 3 to 4 billion USD annually, and for the Great Lakes in the North America, this amount is vary between 128 million USD to 8.6 billion USD annually. These consequences, this economic loss is direct economic loss of eutrophication for freshwater ecosystems. If we included the indirect costs such as greenhouse gas emission, for example, in the US, the direct cost was around 2 to 5 billion per USD per year. The cost related to methane emission from the lakes is around 4 to 9 billion USD per year, and the cost for CO2 emission is around 5 to 20 billion per year USD per year. Total economic cost, that is summation of direct and indirect costs, is around 9 to around 29 billion USD per year. This fact clearly demonstrate that we should control eutrophication. Eutrophication is not a local problem, is not a local concern. It's a global concern that treats fresh water and coastal water globally with a large amount of economic losses across the boards. But eutrophication is not a uniform process. It may differ from lake to lakes, complex interplay between eutrophication and both climatic and anthropogenic factors has resulted in substantial research gap. For example, in understanding the impact of environmental factors on relationship between chlorophyll-A and nutrients. Also, determining dominant nutrient control in chlorophyll-A due to site-specific factors and temporal variation that limit the identification of limiting nutrient. And another important point is using the traditional methods such as TNTP ratio for determining the limiting factor of chlorophyll-A. These methods ignore other drivers such as light, temperature, water residence time, and other microelements in controlling eutrophication. Here we are planned to address these three important points by a collection of a rich global data set on water quality data that gathered across over 14,000 lakes globally, and analyzing this data to better understand these three important research gaps in a global scale. To address these three research gaps, we collected a rich data set from the lakes. Our compiled data set includes around 1 million measurements in more than 300,000 data points located in around 14,000 lakes distributed across 77 different countries globally from 1933 onward. Our data set include chlorophyll-a, total phosphorus, total nitrogen, ammonia, nitrate, nitrate, dissolved oxygen saturation, dissolved organic carbon, total organic nitrogen, total suspended solid, total iron pH, turbidity, lake surface water temperature, sea depth, mean depth, maximum depth, lake surface area, lake altitude, and lake parameter. This figure shows you spatial distribution of our data sets and detail about the chemical, morphometric, and climatic parameter in our data sets. As the main focus of our research was on chlorophyll, total nitrogen, and total phosphorus, we plotted spatial distribution of these three parameters. For example, this figure shows you spatial distribution of chlorophyll-a dataset across the global lakes that include around 300,000 unique chlorophyll-a data points collected from over 14,000 lakes in 77 countries globally. They range in their legend present different trophic states in the lakes based on the Carlson and Simpson suggestion that classify the lakes to oligotrophic, mesotrophic, eutrophic, and hypereutrophic. This figure shows you a spatial distribution of our dataset for total phosphorus data. That again, we classify each lakes based on the total phosphorus concentration to four different trophic acid classes. I mean oligotrophic, mesotrophic, eutrophic, and hypereutrophic. And also this figure shows you a spatial distribution of total nitrogen in our data set that classify based on the total nitrogen concentration according to the four different classes of eutrophication: oligotrophic, mesotrophic, eutrophic, and hypereutrophic. We also calculated total nitrogen to TP, total phosphorus ratio, TNTP ratio, for determining the dominant nutrient that control algal growth in the lakes based on the chlorophyll-a concentration around 20, 27, 45, and 8% of the measurement were categorized as oligotrophic, mesotrophic, eutrophic, and hypereutrophic state. Also, TNPP ratio show N and P co-limitation in 8 and 16% of the investigated lakes. Also, P is limiting nutrient in the remaining lakes over than 76% of the lakes. To investigate the relationship between nutrient and chlorophyll, we used a data-driven model. Generalized additive model to better investigate this relationship between nutrients and chlorophyll. We found a sigmoidal type relationship between chlorophyll and nutrients. This sigmoidal type relationship clearly consists of three distinct regions in the low concentration of nutrient and high concentration of nutrients. Here, it seems that the chlorophyll is not a function of nutrients, and large change in the nutrients and change in the nutrient is not responsible for the change in the chlorophyll-a. The first a small response at low concentration. Here, a small response of chlorophyll-a at low concentration of nutrient. This middle area, we can see a large response at intermediate concentration of nutrients. This region also called acceleration state, and also here a small response again at high concentration of nutrients. This type of relationship suggests that other factors may play an important role in chlorophyll A and nutrient relationship. To better understand the impact of this factor on this relationship, we consider lake morphometric characteristics, example, water depth, lake thermal regions that refer to the stratification and mixing regime in the lakes, climate condition, and water quality parameter to better understand which parameter has a main role in these two areas, low concentration and high concentration of nutrients. A main factor that impacted the chlorophyll and nutrient relationship is lake depths. Rate of nutrient differs among the lakes of different depths, primarily caused by in-lake biogeochemical process such as sedimentation and denitrification that cause uh, loss of nutrient in the water column. This diverse control mechanism could influence the relationship between chlorophyll and nutrients in the different lake types across different landscapes. Therefore, following the method suggested by Kim et al., we use the mixing depths in the lakes to separate them according to three categories: shallow, transitional, and deep lakes, and further investigated nutrient chlorophyll for each class of the lakes, each class of the depth-dependent lakes. Another important factor is lake thermal characteristics. Stratification and mixing regulate nutrient dynamic in the water column. Main factor that impact the relationship between chlorophyll and nutrient. Following this method suggested by Mayberry et al., published in Nature Communication, we classify the studied lakes in 9 thermal regions using lake surface water temperature derived from satellite data. To better understand the impact of other factors on this relationship, we also included the climatic condition. Lake surface water temperature is the main indicator of climatic condition since the lake surface water temperature is since the lake surface water is in direct contact with the climate condition, and any change in the climate condition can reflect it by the lake surface water temperature. We also included two main water quality parameters, salinity and pH. We also included other morphometric characteristics such as lake area, lake volume, shoreline slope and length, elevation, and depths. I mean mean and maximum depths of each lake. In addition, hydraulic residence times and lake catchment area. Totally, we investigated how the relationship between chlorophyll and nutrient is modified by these secondary factors. Our finding, our findings, we classified the lake based on the depths. Our results show that around 12% of the investigated lakes are shallow, as shown by gray circle in these maps. Around 60% of the investigated lakes was transitional, as shown by the purple circle in the on this map, and a majority of investigated lakes were deep, as shown by green circle on this map. Also, we classified the investigated lake by thermal region. We found that around majority of the lake, 55%, are in the northern temperate, around 17% from the northern wall, 13 from the northern half, and remaining from the other thermal regions. And also we found now lake in the southern temperate. We plotted total nitrogen, total phosphorus, chlorophyll, and TNTP ratio against the latitude. As shown in this figure, panel A, panel B, and panel C. Panel A, B, and C, both nutrient and chlorophyll increase with decreasing latitude. We also found where nutrient concentration exceeds the hypereutrophic threshold, I mean northern hot. In this figure, the orange item, we have an increase for TP and TN on this region, but chlorophyll not increase in these regions. That this may be due to nutrient-rich condition of the lakes, since as shown in this figure, in the nutrient enrichment states, chlorophyll did not follow the nutrient, I mean total nitrogen and phosphorus trend. About the TNTP ratio, in the northern hemisphere, the TNTP increase, panel D, this panel, TNTP ratio in the northern hemisphere, the increase with distance from the equator. A main reason may be due to increase in atmospheric nitrogen deposition in high latitude lakes. We further investigated nutrient limitation in depth-dependent lakes. We classified the lake to shallow, transitional, and deep lakes, and for each classes of the lakes, we investigated the main nutrient limitation. We found that in our pool data set, P limitation was dominant in each classes, followed by N and P co-limitation, and finally by N limitation. To better investigate the T and TP ratio in the studied lakes, we consider the trophic states. By considering the trophic state, we found that P limitation is dominant in oligotrophic and mesotrophic lakes across shallow, transitional, and deep lakes. Co-limitation is dominant in eutrophic lake. In shallow, transitional, and deep lake, we have a co-limitation in eutrophic lake. Also, co-limitation is dominant in hypereutrophic state just for transitional and deep lake. Except shallow lake. Shallow lake do not follow this trend for co-limitation in hypereutrophic states. This finding highlights the importance of including the concurrent lake trophic state and lake morphometry in determining the limiting factor for algal growth. After classification of the lakes to shallow, transitional, and deep lakes, for each classes of lakes we investigated, we ran the GAM model, generalized additive model, to understand the relationship between nutrient and chlorophyll. We found a sigmoidal type relationship between chlorophyll and nutrient in shallow lakes, transitional lakes, and deep lakes. This relationship is the strongest in deep lakes. These lakes likely due to losing TP faster than TN. For the shallow lakes, upper and lower limit of acceleration stage intermediate concentration of nutrient here. For the shallow lake, upper limit, I mean this region, and lower limit, this region. Upper and lower limit of acceleration stage for TP, red and blue lines, are more than hypereutrophic threshold and ultra oligotrophic threshold for TP, red and blue dashed line on these figures. For the TN shallow lakes, TN in the shallow lakes do not follow a sigmoidal type relationships. For the transitional lakes, upper limit of acceleration stage, upper limit of acceleration stage for TP and TN here are around 150 and 2,500 microgram per liter, more than hypereutrophic threshold for TP and TN. Also, no clear lower limits can be specified in our model for both TP and TN in the transitional lakes. For the deep lakes, upper and lower limit of acceleration state, intermediate nutrient concentration here. We have both lower and upper limits for total phosphorus and total nitrogen. Both upper and lower limits of acceleration state, for example, for TP are 1.2 and 100 microgram per liter, and for TN are 130 and 1,200 microgram per liter, close to the hypereutrophic and ultra oligotrophic limit of TN and TP in the lakes. This result clearly shows us that in the intermediate step, we have a good relationship between chlorophyll and nutrient. Chlorophyll is a function of nutrient. Any change in the nutrient can increase the chlorophyll-A concentration in shallow, transitional, and deep lakes. Apart from the acceleration stage, I mean low concentration of nutrient and high concentration of nutrient. High concentration of nutrient, I mean hypereutrophic state. Low concentration of nutrients, I mean ultra oligotrophic states. There is no good relationship between chlorophyll and nutrient for shallow, transitional, and deep lakes. This finding suggests other factors may play a key role in hypereutrophic and ultra oligotrophic states between chlorophyll and nutrient relationship. To better understand these factors that play, in the next step, we investigated the impact of thermal regime on chlorophyll and nutrient relationship. We again used generalized additive model and run different model for 6 thermal regions. We found that TP contribute significantly to chlorophyll across the investigated thermal regions. TN is also a significant driver of chlorophyll in many thermal regions, except in the northern region, mainly due to input of nitrogen via atmospheric deposition may be responsible for this pattern, and tropical hot region. The strength of relationship between chlorophyll and nutrient decreased toward lower latitude. Our models show the weakest relationship within the northern hot thermal regions, a densely populated area, suggesting a weak contribution of nutrient to chlorophyll variation here. In such regions where nutrient concentration are high due to excessive anthropogenic activity, they may no longer significantly contribute to the change in chlorophyll as discussed earlier. To better understand the impact of other factors that play a key role in the relationship between nutrient and chlorophyll-A, we investigated the effect of 12 morphometric and chemical parameters in explaining the GAM residual when considering lake thermal regions. We found that saline depths explain the highest percentage of the model residual in 3 out of 6 thermal regions in the northern temperate, northern warm, and northern hot thermal regions. However, saline depths is not statistically significant in 3 regions. I mean, northern freeze, northern cool, and tropical hot. This may be due to saline depths could be more impacted by turbidity arising from non-algal source, resulting from strong seasonal monsoons in tropical hot and permafrost melting in the northern freeze. We also found the lake volume, length of shoreline, average long-term discharge following through the lakes, watershed area, lake surface area, and pH explain a high percentage of residual of the model in the northern frigid thermal regions. Regarding the trophic hot thermal region, lake surface area, elevation, and pH explain most of the GAM residuals. Implication of our result for lake management. From a eutrophication management viewpoint, nutrient reduction-based strategy may no longer sufficient in hyper-eutrophic lakes, where we have high concentration of nutrients, suggesting that other factors may have a key role, as investigated in the previous slides, mainly saline depths, water temperature, lake area. Intervention in shallow lakes might focus on sediment control, leveraging strategies such as reducing sedimentary suspension, since sedimentary suspension results in nutrient suspension in the water column and increase the lake productivity in deep lakes. Efforts should focus on limiting nutrient release from hypolytic layers through techniques like oxygenation or artificial lift stratification. Another important point is over emphasizing one nutrient, mainly phosphorus, without considering co-limitation may undermine restoration efforts, particularly in lake with complex nutrient dynamic. Non-nutrient factors such as saline depths and lake thermal region play a significant role in the eutrophication process, suggesting that physical intervention can complement traditional nutrient reduction methods. Some suggestion: improving light penetration through turbidity management, optimizing thermal mixing regime, employing proactive measures such as climate-informed buffer zone or adaptive biomanipulation techniques to combat the effect of rising temperature. Summary and conclusion, my personal information. I'm Roohollah Noori from Chla, Senior Scientist at United Nations Institute for Water, Environment and Health. Research question: impact of environmental factors on relationship between chlorophyll-A and nutrient, dominant nutrient controlling chlorophyll in different lake depths and trophic states, existence of a sigmoid tight relationship between chlorophyll and nutrients, a strong impact of other environmental factors on chlorophyll and nutrient relationship, especially in low and high concentration of nutrients, dominant impact of water clarity and thermal region on chlorophyll nutrient relationship across the global lakes, considering non-nutrient factors in lake eutrophication management, and considering co-limitation for restoration of eutrophic lake, particularly in lakes with complex nutrient dynamics. Thank you for your attention. Welcome your comment and your suggestion.
Thank you, Dr. Noori, for a really insightful presentation. We will now move on to the Q&A portion of the science talk. A question that I had for you was that if different lakes respond differently to eutrophication, what would you suggest the policymakers focus on?
Different lake. We investigated different type of lakes based on the depth, based on the trophic state for each depth. Generally, the main message is that for the global lakes, in the low and high concentration of nutrients, chlorophyll-A did not follow the trend in nutrient. I mean, increase in nutrient necessarily does not mean that increase in chlorophyll. To better understand the impact of other factors on the low and high concentration of nutrients, we investigated the impact of other factors such as lake morphometry, lake depth, chemical parameter, and found some other parameter explain the variance between the nutrient and chlorophyll on this low and high level of nutrient concentration.
Thank you. And another question I had for you was that you mentioned that eutrophication consequences can amount in billions of dollars of like consequences. Why do you think people aren't focusing on it more if that's how much the loss is?
Do you mean this slide? Yeah.
Yeah, there were 3 slides that mentioned billions of dollars of loss.
Yeah. This slide is the number is from published paper in environmental science and technology. The amount is up to 5 billion USD per year just for the USA. Can you repeat your question? Sorry.
Why aren't people focusing on it more if that's how big the loss is?
Do you mean the amount of the loss?
Eutrophication, like dealing with eutrophication and trying to decrease the consequences of it. Do you think people are dealing with that enough?
I think the eutrophication process in the when we is very complex process and need more studies to better understand this this process. For example, detecting eutrophication using the trophic state index is still there is no global agreement on a trophic state index to determine the stage of eutrophication for lakes and coastal waters. A main message from my study is that the current work to manage eutrophication is not sufficient since many work focus on limiting phosphorus input to the lake, and some efforts have tried to limit nitrogen input to the lake, but our results show that in the high concentration of nutrient, now other factors may play a significant role. Therefore, it's important to understand this factor clearly and think about how we can control this factor to control eutrophication. Controlling eutrophication may have many benefits for human and ecosystem. One benefit is reducing the economic losses.
Thank you. We have a question from Dr. Rohit.
Thank you very much, Dr. Noori. Very interesting presentation. I was wondering, I've been looking into a body of research that is looking at the applications of machine learning to predict cholera outbreaks. And one of the findings is that they found that chlorophyll-a concentration alongside sea surface salinity and land surface temperature are some of the strongest predictors for cholera outbreak risk. And I'm wondering, and that actually achieved like 90% sensitivity in identifying outbreaks. So I was just wondering, given that your work is characterizing the environmental drivers of chlorophyll dynamics to such precision, I'm wondering if you see the potential of this being used for predictive analytics, and if you've looked into that domain at all. Any thoughts on that?
In this research that I presented for you, we just aim to determine the main environmental control that have a key role on eutrophication in different range of nutrients, and to predict eutrophication. We did not aim to predict eutrophication with machine learning models. But in other words, we tried to suggest an open access software for global eutrophication prediction across inland water, I mean lakes, rivers, and estuary. This work is now under review in a journal, and I hope we have the chance to present this research for you here.
Look forward to reviewing that. You know, I think some very interesting applications further down the line than in terms of, you know, looking at waterborne disease prediction and the relationship with chlorophyll-a prediction. So we look forward to collaborating on that down the line.
Yeah, a main problem for prediction for prediction of eutrophication is the lack of the data. For prediction of eutrophication, main challenge is the lack of the data, especially time series data for nutrient concurrent measurement of chlorophyll and nutrient and other factors. For a single lake, it's possible to use machine learning for predicting eutrophication. But for the global lakes, when we have with many complexity in collecting the time series data for fed into the machine learning model to tune a good model with a good accuracy to predict future blooms or future high concentration of chlorophyll and eutrophication in the lakes.
Thank you.
No, that's great. Thank you very much.
We have a question from our colleague Joe.
Hi.
Yes.
So yeah, it's a great presentation. I'm actually quite new to the whole environmental domain, so very interesting for myself personally. So my question is, and perhaps I missed this during the presentation, but in terms of man-made eutrophication, are there any particular regions in your data set that you found were unusually high in terms of that type of eutrophication? That's the first part of my question. The second part is that, are there any types of interventions that would actually have been known to successfully decrease the eutrophication?
I think the main message of this presentation is that overemphasizing on nutrients, mainly TP. This one. Overemphasizing on nutrients would mainly phosphorus without considering co-limitation may undermine the restoration effects, particularly in the lake with complex nutrient dynamics. Maybe, in my opinion, maybe we should study lake. Some suggestion is that I think overemphasizing on nutrients may be a reason that we cannot control eutrophication in global lakes. Another main important is lack of knowledge. For example, this figure told us that in high concentration of nutrient in shallow, deep, and transitional lake, maybe nutrients do not play an important role in chlorophyll. Other factor may be important. If we know this factor, we can limit this factor to control eutrophication. I'm sorry, can you repeat the first section of your question about the data? Yeah.
Yeah. So I was wondering, are there any lakes that you've in your data set? You have a pretty vast data set, and so are there any lakes in particular that stood out to you that had unusually high levels of eutrophication?
No. We just gathered the data from the literature and the published data and from direct contact of organization, governmental and non-governmental organizations to collect the data. We just analyze this data.
Okay. Thank you.
Thank you. One final question I had for you is, you mentioned that you would like to see more studies in this field. Do you have any particular areas in this topic that you'd like to be studied?
Sorry, can you repeat your question?
Yeah. You mentioned that you'd like to see more studies in this topic. What would be the best areas for further research?
Best area for further research? I'm not sure about your question. Best area, I think that Europe and the US may be the best area for further research, since these two regions have a rich data set of eutrophication that can help us to better understand eutrophication and environmental controls and other factors that controls eutrophication in these regions, North America and Europe.
Thank you. Yeah. Thank you again, Dr. Noori, for such a thought-provoking and inspiring talk, and thanks to everyone for an engaging discussion. This brings us to the end of today's UNU-INWEH Science Talk. If you enjoyed the session, remember that all of our previous talks are available on our website and YouTube channel at unu.edu/inweh/science-talks. Feel free to revisit or share them with your colleagues. We'll be back next week with another exciting presentation exploring new ideas at the intersection of water, environment, and health. Thank you for Thank you all for joining us today, and we look forward to seeing you at our next science talk. Have a wonderful day.
Thank you so much for giving me this opportunity to present my research.
Yes, thank you so much for presenting your research.
Yeah.
Bye bye.